It's nice. Okay, so indeed. So I'm a postdoc at the University of Ghent, and I will mostly be talking about work I've done together with Laurens. But I actually forgot to add this picture somewhere. So okay, but I think most people know Laurens van der Straten. So first, a bit of an overview. I will try to motivate it. Why are we interested in spectral functions? And what do people typically do? Then go over a whole bunch of quasi-particle methods, which I think is the coolest part. And then there are a few more recent techniques, and this thing is actually still work in progress. So the paper has yet to be written. So I have way too many slides because I started making this presentation and it kept growing. So I'll probably have to skip over like half of it. But yeah. Okay, so first, why are we interested in spectral functions? The main thing is, well, this is actually a very nice bridge between theory and experiment. So spectral functions really reveal your elementary excitations. If you cool down your system and you probe it a little bit, then you can really kind of measure the excitation spectrum, like the lowest few excited eigenstates, directly, and you can do this experimentally. And these objects also occur quite often. So if you do some calculation in perturbation theory, typically your results will be given or can be reformulated in terms of these spectral functions. And so the plots here are actually like experimentally measured. So there is this inelastic neutron scattering, which I think you just impinge neutrons on your experiment. This was some copper compound, and theory is actually what you would expect if your model realizes exact Z physics. So just if it were some integrable exact Z spin on a half chain, then you would expect to see the following spectral function. And experimentally, they measure something which is, I mean, very closely related, it's almost the same. So you really see this continuum of excitations. There are other methods. There's this ARPES experiment where I think you shine light on your experiment and kind of measure what electrons get excited. But the point to make actually is that, well, okay, this is experimentally measurable and very relevant. And so just a quick matter of definition. What do I mean by spectral functions? Are just general object of this type, right? So you have some state, and you apply some momentum operator. So some superposition of this operator On at every side with some momentum prefactor. You do time evolution, apply it can be the same or a different operator, negative momentum, opposite time evolution, and take the Fourier transform. And then, I mean, this is exactly, if you apply this to the ground state, you actually see that your spectral function measures some kind of density. So it measures, so it's expected to be non-zero if the excitation exists. And well, the amplitude is kind of related to how much of this eigenstate you create when you apply this operator on the ground state. But so it really measures your excitations in a sense, right? So these are the kind of objects we want to calculate, and we want to do this with, well, we typically do this at Ghent with tensor network techniques. So maybe first a very short introduction to tensor networks. So tensor networks are really just, well, networks of tensors. There is this diagrammatic notation where just nodes are tensors with legs sticking out. These legs correspond to the spaces of the tensor. And if you see two tensors connected, for example here, this means that the corresponding leg is contracted over. What you can do is you can chain these tensors together and kind of represent bigger objects. And so, for example, this is an object with 6 legs sticking out. This you can use as an ANSATZ for a wave function, right? And so depending on the dimension, this virtual dimension, this chi dimension that we are contracting over, you can make this larger or smaller. Then you have larger or smaller tensors. And the states that you can then describe by changing the elements in these tensors become larger and smaller. But it also becomes computationally more difficult. Like if you make these tensors very big, you can essentially describe your entire Hilbert space, but this is computationally just not doable. And so in tensor networks, all you're really doing is you're optimizing tensors so that your wave function is some good approximation of some physically relevant wave function, right? So if you want to measure or calculate the spectral function, typically the starting point is to approximate the ground state. You have this variational principle. You just minimize the energy. There are a whole bunch of techniques for this. So if you have a finite system, for example, in the previous case, there was 6 tensors. You can optimize these tensors to minimize the energy. There is an algorithm for this. It's called DMRG. It's very efficient. For infinite systems, where you just take like a whole bunch of tensors and you periodically repeat them. And you describe an infinite system with very few parameters. There's this Fooms algorithm. This works very well. But recently, we also wrote a paper. It's like 2021. Well, mostly done by Marcus and Yuto. It's some kind of gradient descent scheme. I don't think many people know of this paper, but we've shown that for systems where DMRG or Fooms struggles, typically this gradient descent scheme actually drastically outperforms it. And so if you have a difficult problem with tensor networks, it actually takes a really long time to find this ground state, you should consider actually this Grassmann gradient descent scheme. Okay, so then you have your ground state. You apply some operator at a local position, an operator at site n. This is again just a very simple contraction, and then you do time evolution. The way you do time evolution, if you have a finite system, then you just you try to vary these tensors in such a way that you approximate the time evolution, the true time evolution of your system as good as possible. If you have an infinite system, then what you do is you just take like a window of tensors, like n tensors, and you optimize this to kind of follow the time evolution of this local operator. There are a whole bunch of algorithms for this. This TDVP, W2, this Trotter-based TEBD. They all have some time step, and they're all accurate up to some order. But typically, this is not the main source of errors. The main source of error is actually this virtual dimension. So you change these tensors. So you have this virtual space that you contract over. And you can only make this so large to keep these tensors in your system, because it takes a lot of memory. And if you don't make them large enough, then you cannot really capture the full time evolution. And so this really is the crucial approximation. This is where the main errors occur, and this is why the actual time evolution is not really exact. But okay, we have some way of optimizing these tensors, kind of varying them to approximate the time evolution. Typically, you get some kind of light cone, right? If you have your system, you do local perturbation. This kind of spreads to your system, and you can really see this if you measure like the energy density, for example. This is another source of errors. If you have like an infinite system and you only change like n tensors, at some point this light cone will hit the edges. And you cannot really, you would have to grow this set of tensors to keep track of the full time evolution, but this is of course only doable up to some point where, I mean, it just becomes too expensive. But this is typically not really a problem. And then, well, you have this time evolved wave function. You have this at a whole bunch of times. You just measure a different observable, this O, at different sites for at every point in time. So you have these correlators for a whole bunch of times, for a whole bunch of distances, which you then want to Fourier transform. Because if you Fourier transform this is exactly your spectral function. There is already here a small annoying problem. Namely, this is an example of some kind of correlator, some ANSATZ correlator. If you plot this, then you see that this oscillates, but it doesn't really decay. This doesn't go to zero. So if you want to take the Fourier transform, if you want to integrate this, this Fourier transform actually requires knowledge of all times, the signal at all times. So one thing you can do is you can try to fit some function. This is called linear extrapolation. There are some schemes to do this where you just kind of fit your function, you extend it to infinity, and then you can take the Fourier transform. Another thing you can do, and it's actually what we typically do, is just add some Gaussian, e to the exponential of minus epsilon t squared. This will make sure that your signal will decay exactly. And then you know that, well, the action on the Fourier transformed version of this, it just kind of some Gaussian smearing. Well, as an example, you can do this for spin-1 Heisenberg. Spin-1 Heisenberg, I actually will use as an example throughout this entire talk, because this is like some very nice example of a non-integrable model that is still fairly simple. So in spin-1 Heisenberg, you have this stable Magnum excitation, which kind of goes into a continuum of 2 particles, and you have 3 particle excitations. And so you expect that the spectral function has a very sharp peak. You should see this nice Magnum branch. You should really see this in the spectral function. And then it goes into this 2 particle continuum, where you expect this to kind of spread out a little bit. And so this is exactly what you see. So it's a very low resolution picture. But this is exactly the kind of pictures you get. This is the spectral function. You really see this very nice line. This is the stable Magnum mode. It's not an exact line here. It's like smeared out a bit because, well, we did this Gaussian trick, right? This exponential minus epsilon t squared, which makes sure that we can take the Fourier transform, but it's at the cost of smearing this out a little bit. But you really see the qualitative difference between the stable Magnum mode and here where it kind of enters the continuum and becomes unstable. So to kind of sum up, you apply some perturbation, you do this time evolution once, you calculate a whole bunch of overlaps, this is very cheap, and you get this entire spectral function. So you get like your entire Brillouin zone, and you get also, well, in principle, every momenta, every frequency. But there is some limit in the resolution because, well, you only do time evolution up to some finite time. But that's okay. You essentially get all your information that you want with the single simulation. I mean, this is state of the art, I guess. This is what people typically do. If you encounter some spectral function calculated in tensor networks, that's typically what has been done. And so the question is, how can you improve on this? How can you do something else? One way is to directly target the excitations, right? The expression for the spectral function is extremely simple. If you know the exact excited states. So if you kind of can variationally find these, if you can find these eigenstates, these excited states, you can directly reconstruct what the spectral function should be. That's this quasi-particle approach. So what you do is, well, we typically start with some ANSATZ. This is a known ANSATZ there. This is so the intuition behind this ANSATZ is, let's say you have your ground state, which is given by these A tensors. If you now change a single tensor, so you replace like a single A tensor by some B tensor, then you expect the state to still be very low in energy. Right? It's almost it is the ground state almost everywhere, except at some local point where you would change a single tensor. This will still be fairly low in energy, but it's also fairly non-trivial, right? You have this B tensor which has access to this virtual degrees of freedom, and so physically this will be some spread out perturbation, but it will still be fairly low in energy. Right? This would be a very bad ansatz to use for excited states. Because, well, if you only change a single B tensor, this is no longer invariant under translation. This is no longer a momentum eigenstate, which you do expect for excitations. And so then, well, one thing you could do is just take the superposition, right? You just take this B tensor. So you change a single A tensor by a B tensor, and you take some momentum superposition. This directly gives you your ansatz. So it has a very clear particle-like interpretation. It has some, in a way, you're kind of looking at some plane wave, some kind of B tensor, which travels through your system. So you get like a very clear intuition about what is happening there. And all you really have to do is, well, for a certain momentum that you're interested in, you just minimize, again, the energy with respect to this B tensor. So you have your state, which is now parameterized by this B and this K. You just minimize the energy with respect to this B tensor. This is very cheap. So it is like it is just some eigenvalue problem. And you can do this iteratively with some Langsos or Arnoldi methods. And you really get exact eigenstates. So typically when people talk about quasi-particles, they mean these long-lived objects. But here, we really mean, we're really targeting the exact eigenstates. So we really mean, in essence, particles with an infinite lifetime. One more cool advantage is that if you're interested in a certain momentum, you can directly look at solutions at this momentum. So if you contrast this to other methods, then typically, for example, in exact diagonalization, you find the lowest few energy modes. And so if you're interested in a certain momentum, you really need to find you really find a whole bunch of eigenstates that you're not really interested in until you're at the right momentum. Here we really look at this single momentum that we're interested in. Okay, so what do you get if you apply this to spin-1 Heisenberg? You get the following curve. So this is well, this was this time evolution result. And this is the kind of curve that you find if you do this minimization, right? And so you really find some kind of isolated line, which exactly corresponds to the spectrum that you see in the time evolution. But there is some point where it is wrong, right? Because at this point, actually, what we have here is a two-particle continuum. We have this continuum of states, which we don't really capture very well. Because this quasi-particle ansatz would kind of predict that this is some stable mode. And so, in essence, what it's doing here, well, it's minimizing the energy. Right? So it's kind of finding this lower edge of this continuum. So that's essentially what it's approximating. So this is like the first step. And you can actually improve on this further. What you can do is you can actually construct the two-particle continuum. Right? So what we find is a whole bunch of modes, this excited states, and these are stable. These are well defined. So, what we can now do is look at what kind of states would you get if you take two of these kind of excitations. So you can really reconstruct the continuum which lives at these momenta. So the way you do this is, well, the ansatz that you quickly arrive at is, well, there is a whole bunch, there's a part, a contribution in the wave function, where this first particle with momentum k1 is very far from the other particle with momentum k2. They're very far away from each other, and so you would expect that this ansatz is just, I mean, this should be the same tensor, this B1 tensor, as you would find if you just look at the single particle modes. This tensor you already know in a way, because I mean these particles should not really feel each other. There should be this first the single contribution, There should be a contribution where this B1 particle with momentum K1 is to the left of the second particle. There is a contribution where it's to the right of the second particle, times some optional phase, which I will suggestively call S. And there will probably be some correction, right? If the particles get too close to each other, they will probably start to feel each other. And so you do expect generically that there is some kind of correction. So this is your ANSATZ. We know this B1, this B2, this K1, K2. This is given by the asymptotic modes. And essentially what you have to do is you just have to solve this linear problem where your unknowns is this correction where the particles are very close to each other, and this S, which is exactly your S matrix, by the way. So if you do this, you get your entire continuum of two particle states. You get these exact eigenstates. And so you can calculate what your spectral function should be given these eigenstates directly. So you don't have to do any kind of time evolution. All you have to do is solve a whole bunch of eigenvalue problems, which is arguably easier. It's at least nicer in principle. So this is, again, spin on Heisenberg at momentum pi over 10. So pi over 10 is somewhere, I guess, here or something. Like it's right in the two-particle continuum. And you really find this nice smoothed out shape directly. And I find this a very nice result. So this was work done by Lawrence in like 2014. So this is actually a fairly old method, but it hasn't really been used since. And I'm not sure why. One really nice thing is that, well, by optimizing, by kind of finding this correction and this S, you really get your S matrix. This S matrix contains a whole bunch of information. It contains information about what exactly the potential is that these particles feel when they get close to each other. So as an example, here I looked at easing with some longitudinal field. And I just calculated, this is at a fairly small bond dimension, so I would not really take these results too seriously. But nevertheless, I just calculated this S matrix. And you really see these nice poles, which I think are, so this is with some longitudinal field, so it's not integrable. There should be these kind of bound states, which I think correspond to these poles. Yeah, I'm not really sure. I still want to use this S matrix for something, like maybe kind of try to reconstruct the potential that two particles feel when they get close to each other. One bit more speculative thing is you can, these methods still kind of work if you just plug in complex momenta, like nothing really goes wrong. So one question is then, well, if I do this, do I then get like the S matrix, the analytical continuation of this? So what I did here was, again, it's this model, and I looked at this part. So relative momentum 1.25 to 1.75. So really, we should see this pole, I guess. What I find is this. So this is the angle. This is, if you look again, well, just the angle of minus S. And I guess what you see is some kind of branch cut. I'm not really sure. So this is fairly speculative. But the point is, well, it seems to work, and it would be cool to really do something with this. So this ANSATZ, this quasi-particle ANSATZ has been extended to a whole bunch of different settings. So one fairly simple one is, well, what happens when your excitations are some kind of domain walls? If you have like ground states, which for example are labeled by your by 8 tensors. So if you chain all these 8 tensors together, you essentially find the ground state. But you also have a different ground state given by these C tensors. So you can imagine if you have easing, you have a ground state where all spins, for example, point in one direction, but But equivalently, you also have a ground state with all spins pointing the other direction. And there, actually, your ANSATZ, you expect to have some kind of transition between one ground state and the other. And so the ANSATZ you write down is then just some B tensor which lives at the interface. You can also very easily optimize over this. It's completely equivalent. You can also do finite systems. If you have a finite system, you have just, a whole bunch of tensors, but they're all distinct from each other. And so the ANSATZ that you would then write down for an excited state is, well, very similar to an infinite state. You would just expect this to be some momentum superposition, but there is not really momentum anymore. It's a finite system. So you just have like different B tensors at every side. This is easy to optimize over. And what we find, so this is, so we find in practice that this works extremely well. So this is for critical icing. So 20 sites, so you still can do exact diagonalization, you can compare. So it's at the critical point, and I applied periodic boundary conditions to my Hamiltonian. And I then did this with the tensor network techniques for bond dimension 50. So this is fairly low. Yet with this ANSATZ, I get like perfect agreement with this ED results. You really find these conformal towers, and you can count these multiplicities, and this then gives you a whole bunch of information about the actual CFT that describes this model. But more generically, you can just apply it to...
Sorry, about the previous slide,
yes?
Can I ask, this is with periodic boundary condition, right?
Yes, but I only did it for the Hamiltonian. So I used...
No, I was confused because on the previous slide, you talked about open boundary condition.
Well, this is open boundary conditions for my MPS, but I can nevertheless just use this.
Okay, I see. Okay.
Yes, because, well, in practice, these periodic boundary condition MPS methods are fairly expensive, right? If you try to contract these things, it scales like, I think, bond dimension to the fourth or something. So while this is somewhat a natural ANSATZ to use for periodic boundary conditions, so you expect this to require quite a large bond dimension. It also scales much better computationally, and so I'm not sure what the trade-off is. But in practice, we find that it works very well. But okay, it's indeed, this is open boundary conditions, so it's more natural to look, of course, at systems with open boundary conditions. That's what I also did. So this is applied to spin-1 Heisenberg, where I put some weird edge field, because otherwise you have these edge modes. But the very cool thing is that we find, so if you look at the energy density of your excitations, and you subtract your ground state energy density, then you get the following plots. So blue is the first excited mode, orange is the second excited mode, yellow is the third excited mode. So you really find some particle in a box behavior, despite these not actually being particles, right? I mean, spin-1 Heisenberg, you get like a very strongly correlated system, a very non-trivial ground state, yet somehow these excited states really behave, or you should really think of these as particles in this case in a box. Another thing, well, this is actually getting very far away from looking at spectral functions, but another thing you can do is you can make wave packets. So we find these excitations we find for certain momenta. For a given momenta, you optimize this B. And so given a set of these states, you can essentially make these wave packets. If you make a wave packet, you can then let two wave packets collide and kind of measure what happens after the collision. So that's what I did here. So this is a spin-1 Heisenberg. And so the two particle states, so the one particle state, this is a Magnon excitation, and this carries a spin-1. And if you have two of these particles, collectively, they can be in spin-0, spin-1, or spin-2. And actually, depending on the total spin, they actually feel a different interaction. So this can be either attractive or repulsive, and depending on the total spin that they are, that this two particle state is, they actually feel a different interaction. So what I did here was, well, create two wave packets at different position with a certain velocity, so that you know they're going to collide, and you can kind of try to extract where the centrum of this wave packet is. And so I labeled, well, you can do this for different total spin, and you get this blue, green, and red curve. I think it's a bit small. But you get the blue, green, and red curves, and you can then compare this position with what would happen if the particles really just move through each other. So you can really see that well, in two of the cases it's, I think, repulsive, and in the other case it's attractive. This is in perfect agreement also with what you get if you just look at the S matrix. But of course, I mean, this method of making a wave packet and letting it collide is very general. You can also use it just to look at impurities. So what I did here was just take a single spin and change it a little bit. So you change like the local spin, you make it a bit larger, you add some weird couplings. So essentially what you have there is an impurity. Your system is locally a little bit weird. You can just find the ground state of this more complicated system. And you can make a wave packet far away from this impurity, which lives here. So this is like position, this is time. Just make this wave packet here, and just do time evolution. And you know when it reaches this impurity, a little bit of this wave packet will kind of go through the system, just tunnel through the system, through this impurity. A little bit gets reflected. You can measure these reflection and transmission coefficients by just looking at the energy, right? Just look at the energy difference. Well, you look at the energy density. You look at well, how much of my energy is in the upper half of the system, how much is in the lower half of the system. You get these plots, which tell you, well, how much kind of went through and how much got reflected. I think there's still something to do here where we can just directly find the eigenstates, the scatter eigenstates, in combination with an impurity, very similar to like the two-particle collision case. So this is something I would like to do. But now I only have this dynamical scattering results. Fairly important, you can actually use this quasi-particle ANSATZ also in two-dimensional systems. So the easiest way to do this is, well, you can approximate, you can just look at cylinders. If you have a cylinder system, you can kind of approximate this by a 1D system. Well, this is a 1D system with long-range interactions, and then directly these methods will work. But you can also, if you have a PEPS, which is like the 2D analog of like well, the 2D ANSATZ, tensor network ANSATZ. There you also have this quasi-particle ANSATZ. You can also do this optimization procedure. It's a bit more difficult, but this will give you your dispersion relations. There is no way, as far as we know, to get the two-particle states. So I don't think anyone has ever reconstructed this two-particle continuum in 2D. But the one particle you can do. So this picture is very nice, I find. This quasi-particle picture is really cool, but sometimes it really just fails. And the reason it fails is, well, we really need some isolated branch. You really need, in order for this method to approximate the eigenstates very well, you need some kind of gap between, well, the ground state and the excited state, but you also need some gap between the excited state and the continuum above this. In those cases, you can really approximate these states very well. But for example, here, in this region, you have this continuum, and there your ANSATZ is not really well suited to capture this. And so, well, it's variational, so it will kind of try to find the edge, but it will never find it very well. And this is a bit problematic. So one example where it just totally failed was, there was this model which was critical, and it had a cubic dispersion relation. Right, so the energy is just momentum cubed. And there, if you just look variationally, the lowest energy states are actually multi-particle states. And so essentially what you find is some flat band. You never find this nice cubic dispersion relation. You will never be able to detect it. Also, so while we were able
Sorry,
to...
what model was that?
Well, it was some supersymmetric spin model. So it was some spin model which was argued to have some supersymmetry in, like, I think the continuum limit, low. I can look it up. But it was some toy model which is expected to be supersymmetric. And well, we wanted to find this excitation branch, but well, purely variationally with this eigenstate, you can't really seem to capture this. So one way around it there was to just minimize the variance. You look at different energies, different momenta, and like minimize the variance around this point. So for a given energy and a given momenta, you can kind of try to find the lowest variance state, and then you really see this this cubic dispersion relation. You can kind of see. But this is very expensive and also very ugly. But well, it kind of worked. But another limitation, so we could construct this 2-particle continuum, but you can never really do the 3-particle continuum. So there is some obstruction. Just if you work it out numerically, there are like an infinite number of asymptotic possible contributions if you look at 3-particle states, because you have conservation of momentum and conservation of energy. But if you look at 3-particle states, this is not enough to limit your asymptotic contributions to like a finite set of possibilities. So it's just numerically that I think we're fundamentally limited to just 1 and 2 particles forever. Okay. So then this was the whole quasi-particle part, which sometimes failed. And so you really need some kind of method, some kind of thing to do in cases where it fails. Can we still improve on state of the art? Can we still improve on these real space methods somehow where these quasi-particle things fail? And that's how we arrived at these momentum windows, which was a recent paper. This is not a paper. This is an example where the quasi-particle ansatz failed. This was some Hubbard chain where, well, people are interested in this peak. So if you look at the spectral function, this is some peak of very large spectral weight. But purely variationally, you just find like the lowest energy states, which does not correspond with this peak. And so how would you study this mode? Well, I think you really have to look at the structure factor. You really have to do some kind of time evolution, do this integration, and just plot this. And so this is also a very difficult model because, well, already it's some Hubbard chain. So it's essentially a 2D system that we're approximating by a 1D system. So you really need a very large bond dimension to approximate the ground state. And to then do time evolution on top of this is very challenging. And that's, I mean, you really want something better than just the conventional approach of doing like a local quench and doing this time evolution. And so the idea or the insight we had was, well, your spectral function is a momentum object, right? You apply some operator to your states that it's a momentum eigenstate. You do time evolution. So this property, I mean, this is always true. It remains a momentum eigenstate. And then you take an overlap with something with this. Well, this is still something with the same momentum. Right? It's like the conjugate of something with the opposite momentum. So the idea was that maybe, I mean, if we just do time evolution and we keep working at a certain momentum, we could get a larger precision. There's another intuition there. If you remember in these real space methods, you do like a local quench, you do time evolution, and you essentially get your entire Brillouin zone, right? You get your spectral function for every omega and for every momentum. So this wave function, this time evolved wave function, must contain a lot of information. Whereas here, if we keep working at a certain momenta, if we keep doing this time evolution and we pursue this momenta, at the end of the day, you will only have information of the spectral function at this momenta. And so just the fundamental object you're working with here kind of should probably contain much less information. Was kind of the intuition. And so the ANSATZ you then quickly write down is just, well, do the same as in the original case where you optimize some window of tensors to kind of track the time evolution, but at the same time, take like a momentum superposition. So you take a superposition of this window at starting at every possible site with some momentum prefactor. There are some tricks you can do to keep this numerically fairly okay. And well, then just do this time evolution. But very similar methods to the typical real space approach. And so this is what you get. So this is for Spin-1 at pi over 10 again. So the black curve, which is kind of covered by the orange dots, is just some benchmark simulation. So you look at a simulation with an extremely large bond dimension, extremely small time step. So this is, I mean, this is pretty much exact. But then you can repeat the simulation with a much smaller bond dimension. And d equals 50 is probably not enough to really capture this time evolution. And this is also what you see. I mean, if you look at this real space approach, you see that, well, you get this deviation. This is not very accurate. But if you keep working momentum space, then you actually see perfect agreement. So this was very encouraging. This means that actually, with comparable numerical cost, we get a much larger precision. But of course, I mean, you only have this precision, you only have information about a certain momentum, right? This is pi over 10. Whereas the real space approach gives you your entire spectrum. So in a certain sense, these methods are complementary to each other. Like what I guess you typically would or could do is just use the usual approach to get like a rough picture. And then if you're interested in a certain point, you can use this momentum space approaches to get like a very nice precision plot. The computational cost, so it's a little bit more expensive. So it scales, there's like an extra linear factor in like the size of this window. But this is fairly okay. Like the typical limitation is the scaling in bond dimension, the scaling in like the dimension of this leg that you contract over. And this is equivalent. So it's the same for this momentum window approach as the usual like finite window time evolution approach. We also looked at a more challenging model where, well, there is no benchmark simulation. So it's not really, I mean, this is really what people are interested in. It's some J1, J2 model where people are interested, if you tune this J2 interaction with just like, I think your next nearest neighbor interaction, this should, if you make this larger, the question is, does the gap kind of close and does it become like a gapless spin liquid? Or does it remain gapped? And this is essentially what we did here. We looked at J2 equals 0, then there should be this very large gap. And then if you look at J2, if you make this larger, you kind of see that this gap gets smaller and smaller. But of course, I mean, this is a cylinder, a 6-leg cylinder. So you still have like very large finite size effects. And so the gap remains, I mean, for a 6-leg cylinder, it remains finite. So the question is, of course, what happens if you look like an infinite system, like a full 2D system, does the gap close then? But this is, well, way too difficult to do with these MPS methods. There you really need PEPs. But this is an example where such a momentum approach is very useful because we actually know at what point this gap should close. So people are really interested in the spectral function at this particular momenta. This particular momenta should correspond to the gap closing. So there you're really interested in this fine-tuned simulation. Another thing is I was actually hoping to add a plot here, but I mean the simulation wasn't finished yet. So there is actually another entire class of methods to calculate spectral functions, but it's not used very often. And it's basically built on equation 16. It's just recognizing that if you calculate this quantity, essentially what you're doing is you're calculating the overlap of your state with like the inverse of well, if you're interested in the quantity at z, it's z minus h inverse acting on s, and maybe you can just find this state. So you really just iteratively try to calculate the action of the inverse of z minus h acting on s. If you do this for a certain z, then and you then calculate this overlap, and look at, and you really get the spectral function as well. And with these momentum window approaches, you can also do this at a so it does work. You can do this at a certain momentum. Okay. Then the last part is about time evolution operators. So there are a whole bunch of approaches, a whole bunch of ways to do time evolution in tensor networks. Like this TDVP, you have this TEBD, but so typically what we're doing is TDVP. But if you work out, if you just work out how this would scale for such a momentum window, then this actually scales extremely badly. So this is not what you want to do. So you really need something else. And so the other typical approach is you represent, or you try to, so you really approximate your time evolution operator as such a tensor network. So it's called an MPO. And just well, it's a 1D chain of these 4 leg tensors. And what you can do is you can apply this to your state. Your virtual dimension, your bond dimension will increase, so you have to truncate this, but this is one way of approximately doing your time evolution. And the question we had was, can we actually improve on the state of the art there? So the typical way that you could do this is, for example, with some Trotter decomposition. Right? If you do some Trotter-Suzuki decomposition, you really get an object of this form. But we were hoping to do better. And the way the starting point was to look at your Hamiltonian in MPO representation. So you can represent very generically almost any Hamiltonian. So any Hamiltonian of this form of equation 19, you can represent in such an MPO form. So this is an MPO with virtual dimension 3. And if you at minus infinity have like some boundary vector, and at plus infinity have some other boundary vector, and then and in between you just repeat this kind of tensor. So this virtual dimension 3 and the C, D, A, and B are physical operators. You apply this, you calculate what this is. This really is just exactly equation 19. So it's just some other representation of this equation 19. Another way of thinking about this is as some finite state diagram, where at minus infinity you have the state HL, which we call 1, and at plus infinity you have the state HR, which you call 3. And just at every side you can either remain at the same position. So if you're at state 1, you can apply your identity operator, you remain at 1. Or you can, for example, transition to the last state by applying operator D. And once you're in the last state, there's no going back. So it's strictly increasing. You will use this. It's just another representation. So now, why is this useful? Why do we care about this? Well, it turns out that there is a very simple way of turning this expression into a time evolution operator. So the idea is basically, well, instead of going to some last physical state where you kind of stay, you just loop back to the first state. and you multiply by tau. So another way of thinking about it is just you take your last column, you multiply by tau, and you add to the first column, and then you remove this. You get exactly this expression, which is an MPO of 1 dimension 2. And if you contract this, then what you see is that in first order, you really just again have your Hamiltonian, but you get a whole bunch of higher order terms for free. You get like a quadratic term, so you get like a quadratic term of your Hamiltonian, but only all disconnected parts. So where the Hamiltonian, if you like have a nearest neighbor operator, where they don't overlap.
I mean,
Yeah. Wait. Okay, that's someone's talking. But you also have like a whole bunch of higher order terms. Exactly. And the cool thing about this idea is that you can generalize this to higher orders, which I don't think was known yet. So if you look at if you want a second order time evolution operator, what you do is you start out with your Hamiltonian and just you square it. This is easy to do, and you get this kind of very big operator, where you kind of want to do the same thing, right? This trick of, instead of having 3, which corresponds to the idea that your Hamiltonian has been applied, you want to loop this back to 1 and multiply by tau. Here, what you want to do is, well, you want to do the same thing for for your Hamiltonian terms, but you also have like a whole bunch of connected clusters, connected terms, and you want to multiply this by tau squared. Well, okay, it's very difficult to explain, but it's actually fairly easy in practice. So it's okay. If you have this kind of operator, we can represent it visually as this kind of finite state diagram, and these states 1, 3 and 3, 1, they kind of correspond to your Hamiltonian being applied once. So instead of continuum with this diagram, what you want to do is you just want to loop back to your first state and multiply by tau. That's like the first step. Just loop back to your first state and multiply by tau. Well, you have it occurs twice. To avoid some double counting, you just multiply by tau and divide by 2. And then, well, this 3-3 state, this corresponds to like a connected cluster of operators, which is like quadratic in your Hamiltonian. So you want to loop back to 1, 1 and multiply by tau squared. So this is the next step. And this gives you this expression. This is an operator. It's an MPO. It's bond dimension 6. And it's exact up to second order. And it contains a whole bunch of higher order terms, and it contains these exactly. And so this was the main idea. And this is what we've been working on improving. So one quick improvement is, well, you can generalize it to any order. So there is some very simple pseudocode. You implement this and you have your operator for any order. But there is also quite a bit of redundancy in this operator. There were some similarity transform that you could do, and some ways of removing rows so that you get exactly the same operator, but in a more compact expression. So this is, instead of having this bond dimension 6 MPO, you can actually turn it into an equivalent bond dimension 4 MPO. And then as a last step, you could actually play with, for example, this is a second order MPO, so you can imagine adding or subtracting cubic terms, which will not actually affect the actual error, so the scaling of the error. You can exploit this to further compress or make this operator more exact. So this quickly gets fairly involved, and you get these very difficult equations, but nevertheless, in the end, we end up with something which is still correct up to second order. It's bond dimension 3. And it also contains a whole bunch of terms that are cubic in time and which are correct. And so, well, first you can do kind of some benchmarking to check that indeed scales correctly. There's some error measure, and if you look at different time steps, you really see that this error measure scales correctly. But it's also useful. So this is not immediately evident. Just because it's accurate doesn't mean it's fast. But in practice, if you do some kind of simulation, and you do the simulation with like a first order, a second order, and a third order MPO for like different time steps, you can get this kind of curve. Fidelity density, it's also just some measure of precision. And so you see that if you spend like 10 hours calculating with your first order MPO, you only get something of which has an overlap fidelity density of 10 to the minus 5 with the exact evolution. Whereas, I mean, you can quickly do much better with like some second order and third order MPO. And this is exciting because actually in literature, what people have been doing is always been using some, well, with MPOs, have almost always been using some first order MPO. Whereas we actually see that you get drastic improvements by going to higher order. And so that's what we're writing the paper on. But it's, I mean, it's not yet out. So also looked, I also repeated the same thing for a more difficult model, a cylindric model. Where you see that just going to higher orders is not necessarily better. So this is first order, but actually the best thing you can do apparently for this model is just to stay with second order and not really go to third or fourth order. But this is model dependent because it kind of is controlled by, so different models will result in different computational scalings for these constructions. But I think in general, the second order is always going to be magnitudes better than the typical first order approach that people have been using. Yeah, okay. So a bit of a conclusion. Consider these quasi-particles when you're calculating structure factors, but not just structure factors. I mean, consider this quasi-particle picture for a whole bunch of non-equilibrium physics. Because, well, it's very satisfying to recast something in this quasi-particle picture. But it's also very powerful. And we have a whole bunch of methods for doing this. And I don't think I mean, it's being used enough. I'm not sure why, but I don't think it's really being leveraged to the best extent. Also, I mean, if you are calculating structure factors, consider enhancing your precision by really keeping this momentum there. Keep working in momentum space to really push your precision a bit further. And also, if you want to do time evolution, these higher order time evolution MPOs, they really make sense. I mean, in practice, this can give you orders of magnitude better precision for the same computational cost. And that's, I mean, that's pretty much the end of.
Okay, let me just start recording.